And to get started, I just want to define what solar testing actually is. And it is the exposure of a specimen to either natural or artificial illumination, which approximates natural sunlight. And there's a few different reasons that we perform this kind of testing, but essentially it's to simulate stress on a material caused by a solar load. And you can see I've included some examples here for some damage that we see caused by solar loads. Up in the top left-hand corner, you can see a steering wheel that's obviously gone through some cracking and embrittlement that's been caused by the sun. Another thing that we see quite often is color fade. So if you look in the bottom left corner, you can see a good example of sun that's come through the window and caused some color fade on those hardwood floors. And we also see some display errors sometimes on outdoor displays, such as displays on gas pumps or outdoor televisions. So if you look up in the top right-hand corner, you can see an example of some errors occurring on that display. And then also, oftentimes you'll get warpage from a solar load. So if you look down at the bottom right-hand corner, there's a picture of some warpage on siding that's been caused by sun exposure. So there are a few different types of solar testing. Mainly we've got natural exposure, fluorescent UV, xenon arc, infrared, and then full spectrum solar simulation. And these all focus on basically the same concept, but they're going to utilize different types of equipment, and then also different types of tests oftentimes are going to focus on different portions of the solar spectrum. So to break down that spectrum, here is a diagram of the solar spectrum. And we can see at the low end, we've got UVC radiation. And this is mostly used for sterilization. And UVC radiation is actually filtered out by our atmosphere. So it's going to fall outside of the range of most solar simulation systems. And typically, if you do UVC testing, you're really just using that for sterilization. So there's actually specific specialized equipment that's used that outputs just that UVC radiation. Now, if you move up in the spectrum a bit, we hit UVA and UVB. And these are typically the main cause of both part deterioration and also color fade. And then if you move further up in the spectrum, we've got visible light, which is typically the secondary cause of those same factors as well, both part deterioration and color fade. But it is important to note that different materials and different pigments are going to be affected differently by different portions of the spectrum. So while you've got some pigments that might experience a lot of color fade down at 300 nanometers, you're going to have other pigments that experience color fade more from that visible light portion, maybe up in the 500 nanometer range. So a lot of solar simulation equipment is going to try and focus on a relatively wide spectrum. And then if you move up in the spectrum even more, we reach the infrared light portion, and this is what's going to contribute most of the heating effects of solar radiation.